All right, so we're going to pick up now with our next section on the cell membrane and transport chapter. And we're moving into our second main part, which is going to cover different types of processes that cells can use to either import or export things relative to their environment, right? So we've got a bit of a long section on that, and then eventually we'll finish out the chapter by talking about different types of cell to cell connections. So, before we start moving into transport processes, we've got to get a little bit of background on how matter works. Excuse me. So, it turns out that all matter, as long as you're above absolute zero, is in a state of constant random motion. So, you can think about any kind of particle in the universe, anything that has mass and takes up space, is continuously vibrating back and forth in space randomly. Now, that's going to occur as long as you're above absolute zero, which is really, colder than any sort of natural condition on Earth would ever be. But as long as you're above absolute zero, negative 274 degrees Celsius, all matter in the universe is going to have some motion. So temperature then is one way to think about measuring molecular motion. Obviously, the higher the temperature, the faster those particles are going to vibrate back and forth in space. So, as long as you're above, like I said, absolute zero, movement exists. And I guess I said negative 274, it's actually negative 273, close enough. These particles are moving back and forth in space. Now, in terms of transport processes, cells can use one of two main ways of moving things in or out of themselves based on whether or not it requires energy. So, passive transport is a mechanism that cells can use to move things in or out that is free of energy, does not require energy. No ATP required to do passive transport. And as you can see on the slide, there's about three different types of passive transport that we're going to talk about. We also then have what's called active transport. So we wouldn't have passive if we didn't have active. So we have active transport, which is a way to move things into or out of a cell that does require energy. And then finally, we also have something called bulk transport, which includes both exo and endocytosis, which in terms of energy are a bit more similar to active transport because they are very energetically expensive processes, but they're reserved for only the largest of molecules to be moved in or out of a cell. So passive transport, like I mentioned, is a way to move things into a cell or out of a cell in which ATP is not required. It's free. And so in order for passive transport to be feasible, the things that are moving into or out of a cell have to be moving with their concentration gradient. Now, whenever I say with a concentration gradient, what I'm talking about is moving from high concentration to low concentration. That's going with the gradient. That's going with the flow from high to low. Now, I'm rhyming for some reason, don't know why. But as long as you're going with a concentration gradient, ATP is not required. All right, so think about getting into like a canoe or a kayak in a river. As long as you're willing to go downstream, it's free. It does not require energy. You just go with the flow, and you don't have to paddle, you don't have to spend energy, you just kick back and enjoy your favorite beverage, and you go with the flow. Passive transport's the same way. Now, on the other hand, if you want to go upstream, if you want to go against the current, go against the flow, or in this case, go against the concentration gradient, now you have to be willing to spend energy, and that's where the second kind of big category of transport process is going to be when we get to that here in a few minutes. So diffusion then is a passive process. So what do we know about passive? It does not require ATP, and it goes with the flow from high to low concentration. Diffusion is movement from high to low concentration. Now, we can talk about things diffusing in terms of various types of particles. We can talk about water diffusing, which is what osmosis is. We can talk about diffusion that requires help in the form of transport proteins. And we're going to cover all of those here in the next few minutes, but they are all types of diffusion. All the passive transport we're going to see is based on a type of diffusion where things are going from high concentration to low concentration and in which energy is not required. All right, so eventually, if diffusion is allowed to continue and these particles spread out in space from high concentration to low concentration, eventually they're going to become balanced in various places, right? So if things are spreading out from high to low concentration, eventually the concentration in those two places is going to be equal. And at that point, we've achieved what's called equilibrium. Now, equilibrium does not mean that these particles stop moving, right? Because again, like as I said before, as long as we're above absolute zero, these particles are always going to continuously vibrate back and forth in space. But if they're at equal concentrations, there's no longer a net change in concentration on, say, two sides of a membrane, right? Because as soon as one side is higher than the other side, diffusion takes place, they spread out, and equilibrium is achieved, okay? Now, this is a quick look at simple diffusion. So imagine we've got a cell here, And just kind of arbitrarily, I'm going to say the bottom down here is the cell cytoplasm, and up here on the top is the extracellular environment. And so outside the cell, we have a high concentration of whatever these blue particles are, and these blue particles are allowed to pass through the membrane and spread out in space such that they're going to eventually have the same concentration inside the cell as outside the cell. All right, so some requirements here. Number one, going with the flow, going with the concentration gradient. And number two, these particles have to be able to get through this membrane. And that is not an inconsequential thing, right? We talked about this back in our first section of this chapter. For molecules to pass through a membrane like these are, these molecules have to be hydrophobic or nonpolar, same thing, right? So they've got to be able to go through this massive network of hydrophobic tails in order to go from the outside of the cell to the inside of the cell, or vice versa if we're going that way. So if we're dealing with things like amino acids or ions, simple diffusion is not going to work because those molecules are polar, they're partially charged, and for that reason not able to get through the phospholipid bilayer. All right, so this again is a type of just illustration of diffusion, looking at oxygen, CO2. Turns out water doesn't really diffuse through a membrane all that easily, so I've always kind of wondered why they included that on this slide, because water is by definition hydrophilic, so it's not able to cross through this hydrophobic barrier. Occasionally a water molecule or two might be able to sneak through just because they're small, but it's certainly not any great degree of water movement across that cell membrane, at least using simple diffusion. Now, if we're talking about rate of diffusion, generally speaking, cells in our bodies or cells in other environments want to be able to do as much diffusion as quickly as possible to get the things they need and get rid of the things they don't need. All right, so evolution has built cells to be able to utilize maximum rates of diffusion. Now, temperature is not really something that cells really take advantage of too much, because if a cell were to somehow heat itself up just to maximize diffusion, that would be a bit counterproductive, because actually the cell would kill itself, right? High temperatures kill cells, so that would be kind of a very dangerous way to try to increase the rate of diffusion by just increasing the temperature, right? Now, on the other hand, concentration gradients are something that evolution has been able to tinker with in order to create higher rates of diffusion. So for example, if you have one side of a membrane that has just an enormous concentration of some type of particle, and the other side of the membrane has like only one or two of those particles, you've got a really big concentration gradient. Those particles are going to spread out very quickly in space. You're going to see a high rate of diffusion under those certain circumstances. Another factor which influences diffusion is the distance across which the substance has to travel. So if you've got a situation where these particles have to travel a really, really long way, relatively speaking, it's going to take a bit longer, which is kind of intuitive, right? If you have to go a long distance, it takes longer than if you have to go a short distance. And so for a lot of reasons, cells in our bodies are set up such that the distances the particles they're diffusing have to travel is relatively short, and that's going to help us maximize rate of diffusion. So for example, if you look at oxygen transfer from the alveoli or the air sacs of your lungs into your blood, that O2 gas, that O2 molecule, only has to cover 2 cells to get from the lung into the blood. And that's a very, very short distance. And it turns out, on top of that, these cells are very flat and very thin, so the oxygen really doesn't have to travel very far. Therefore, it's able to get into the blood pretty quickly from the lungs. And the opposite is also true of CO2. Another factor which I don't have on this slide, I probably should add it at some point, is surface area. A lot of, especially respiratory surfaces in different types of animals, are set up to have maximum surface area, so they're able to do maximum gas exchange with the environment. All right, so we talked about this back in our last chapter, but the reason why we don't see too many really, really big cells is that A, they wouldn't have very much surface area, and B, they would have too much volume to function effectively, and for that reason diffusion would take simply too long. The other thing to think about here is what the phospholipid bilayer is doing when diffusion is taking place, right? So the phospholipid bilayer we talked about back in our first section of this chapter is selectively permeable, but because we're using simple diffusion and because we're not using energy, the bilayer is only facilitating the movement of particles either in or out. The direction is based on concentration gradient. Wherever that concentration is higher, that place is going to lose particles. Wherever the concentration is lower, that side is going to gain particles. That's not something the membrane can deal with too much. All the membrane does is decide who gets to pass through and who doesn't. And so the direction those things are passing through and the rate at which those things are passing through is determined by concentrations rather than by the membrane itself. Now, our second type of passive transport, we just looked at simple diffusion, but our second type of passive transport is facilitated diffusion. And so if we just simply look at the term facilitate, that term just means to help, or to allow, or to permit something to happen, to assist something in happening. So then facilitated diffusion is literally diffusion with help. Things are going from high to low concentration, and there's some kind of help involved somewhere in some way, shape, or form that's going to make that diffusion happen or facilitate that diffusion to happen. So in the case of particles that are hydrophilic, particles like ions, amino acids, carbohydrates, proteins, those things are not able to cross the bilayer directly because they are hydrophilic, and of course the bilayer is primarily hydrophobic. So if those particles need to get into a cell or out of a cell without the use of energy, we're going to be dealing with facilitated diffusion. And specifically, the thing that's doing the facilitation is a type of transport protein. These transport proteins allow things that are charged or polar to get out of a cell or into a cell, going with the concentration gradient, again, still going with the flow, not using ATP, but they allow these things to go into or out of a cell where otherwise they wouldn't be able to do these things. Right? So this is still passive transport. This is still going with the concentration gradient, no ATP. And we're going to be using one of two types of proteins here, either a channel protein or a carrier protein. Now in this picture looks a lot like a channel protein because we just have basically a gateway for chloride ions to go into a cell or out of a cell based on which side of the membrane has more chloride ions. So going with the flow still, right? So this is just like a doorway where things can go out of a cell or into a cell based on the concentration gradient. Carrier proteins are a little bit different. Carrier proteins actually have to physically bind to whatever it is they're transporting. And so for that reason, carrier proteins, especially if they're trying to move a lot of substance, can sometimes become saturated to the point where the cell actually has to wait for particles to cross the membrane because there's a limitation on how many transport proteins are actually there. But in both cases of channel and carrier proteins, these proteins are very, very specific. Right? So if a channel protein allows chloride ions to move, it's not going to allow sodiums or potassiums or calcium ions to move. Or if a carrier protein is moving glucose, it's not going to be able to move anything else. Right? It's very, very specific to only the one substance that they're going to allow to move across the membrane. So particularly here, again, just kind of recapping facilitated diffusion, we are dealing with things that are polar, hydrophilic, charged. In other words, things that are not able to cross the membrane on their own, but if the protein is there, they are going from high concentration to low concentration, and ATP is not being spent to do so. So again, this is a channel protein. Particles are moving, in this case, into a cell, in this case, out of the cell, going with the flow from high to low concentration. Same thing over here, high concentration, low concentration. So we know we're not spending energy, but because these particles are presumably hydrophilic or charged, they have to use these proteins to get across the membrane because otherwise they wouldn't be able to go through the bilayer. So carrier proteins, again, very specific, do require a concentration difference because, again, it's driven by passive transport, no ATP being spent here at all. And they can become saturated to the point where, essentially, at one point in time, all the carrier proteins in a cell could be in use, and so other particles that need to move across the membrane have to wait for their turn. So it's a little bit different than a channel protein where the molecules just kind of travel one right after the other in a line into the cell or out of the cell. With carrier proteins, other particles that need to move have to wait their turn to get across the membrane. All right, so this is a good example of a carrier protein. We've got these molecules outside the cell, high concentration out here, low concentration inside the cell. These particles are binding to a carrier protein. What do we know about proteins? Anytime anything ever happens to a protein, what does it typically do? It changes shape. Sometimes irreversibly, sometimes it denatures, but in this case, we're not quite going that extreme. We're going to bind these particles to the protein, therefore the protein changes shape, and as that protein changes shape, it's going to move this purple square particle from the outside of the cell to the inside of the cell. It's going to drop it off or release it, and so when this particle goes off the protein, what does the protein do? It returns back to its original shape, and it's going to pick up the next molecule in line. All right, so you can imagine that if a cell only had one carrier protein for this purple square molecule, it would take a really long time to move all of these into the cell. Now, it turns out that's not usually the case. Usually cells have multiple transport proteins for various substances they need to deal with, but in a hypothetical scenario, they could be saturated, and particles then would have to wait their turn to get across that membrane. This is another good example. This slide shows basically the same thing. Particles binding to a protein changing shape, particle being dropped off inside the cell, protein going back and taking on its original configuration or shape. Now, our last type of passive transport is called osmosis. And this is the one that sometimes is a little bit confusing to people, but it really shouldn't be. right? Because all osmosis is diffusion of water. So water goes from where there's proportionally more water to where there's proportionally less water. And by that, I don't necessarily mean just sheer volume, but we're dealing here with concentration of things in that water. So whichever side of a membrane has a higher percent composition of water is going to lose water, and whichever side has a lower percent composition of water is going to gain water. Water goes from where there's high concentration of water to low concentration of water. All right, so that's really all it is. In this scenario here, we have these two beakers connected by this tube in the middle. This tube has a membrane in the middle of it, which allows water molecules to go back and forth, but not sodium or chloride ions to go back and forth. So having initially the same amounts of water in these two beakers, if we add salt to one, that's going to draw water from the other one toward the one that we just added the salt to. Because, you imagine if these are both initially 100% water, right? And you add some salt. Now this one is 95% water and 5% salt. We've got 100% water here. We've got 95% water here. We know salt can't go back and forth. So the only other alternative for transport in this case is for water to diffuse from the 100% side to the 95% side, from high concentration to low concentration. Just like we talked about before, only now the things dissolved in the water are not moving, and the water itself is the thing that's actually moving across the membrane. All right, so that's kind of the key thing with osmosis. Now, whenever we deal with things with water dissolved in other substances in that water, we are dealing with what's called a solution. All right, so a solvent then is something that does the dissolving. Something that dissolves something else is a solvent. The thing that gets dissolved in the solvent is called a solute. So solutes get dissolved in solvents, and when that occurs, we have then what's called a solution. Right? Solutes dissolve in solvents, and that creates a solution. So we should be very familiar with those terms as we move forward through these next couple of slides. Another way to describe different types of solutions then is based on their tonicity. All right, so tonicity then, we got to define that term. Tonicity is a tendency of a solution to either gain or lose water. All right, tonicity is the tendency of a solution to gain or lose water. So a hypertonic solution is going to tend to gain water, and a hypotonic solution is going to tend to lose water. And if two solutions are isotonic, then they have the same concentration, and at that point they're in equilibrium. The particles of water are still moving back and forth, but they're doing so at equal rates, so there's no net change in the amount of water on either side of the membrane. All right, so hypertonic solutions. If we look at that last slide for a second, my scenario where we had 100% water versus 95% water, 5% salt, this solution over here was the hypertonic one, and this solution over here was the hypotonic one. So because we have more water here proportionally than here, water moves from the hypotonic side toward the hypertonic side. From hypo to hyper until equilibrium is reached and both solutions are isotonic compared to each other. If we're dealing with a description of these terms, hypertonic always has relatively more solute compared to hypotonic. Hypertonic has relatively less water compared to a hypotonic solution. And again, water always goes from the hypotonic side toward the hypertonic side. All right. Now, because water is a partially charged molecule, it's polar, it's hydrophilic by definition, it is water, it's not able to cross a phospholipid bilayer. So in reality, when water moves across a membrane, it actually does so more in the form of what looks kind of like facilitated diffusion, where water uses what are called aquaporins to move across a membrane. So for example, in our kidneys are made up of roughly 1 million or so what are called nephrons. Each kidney has about 1 million nephrons, and these nephrons, and in certain parts of the nephrons, are essentially tubes that can contain various numbers or concentrations of aquaporins. So if you need to have a lot of water reabsorbed back into your blood, you need a lot more aquaporins to do that. If you're trying to get rid of water in your urine, try to produce more urine, then you're going to have fewer aquaporins so that water is able to leave the body more easily. So aquaporins actually allow for osmosis in our kidneys, which is a really, really important job for them to do. So again, osmosis is diffusion of water. We talked about tonicity, the tendency to either gain or lose water. And so that brings us to the idea of osmoregulation. Osmoregulation is a very, very important concept for all organisms. It doesn't matter if you're a plant, a bacterium, a fungus, a protist in any sort of environment, or an animal. All these organisms have to deal with water balance. And whether it's through diffusion or a more Facilitated diffusion sort of a thing depends on the kind of cell you're dealing with, but it's a very, very common problem that organisms have to solve is dealing with water balance so that they're not going to have too much water in their bodies or not enough water in their bodies or in their cells. That's a really important concept. Now, another thing to think about here is what kinds of cells like different kinds of environments. All right, so if we look at a plant cell versus an animal cell versus other kinds of organisms, the general rule of thumb here is that anything that has a cell wall likes to be in a hypotonic environment. Things that have cell walls like to be hypertonic to their environment, and therefore the environment is hypotonic. For that reason, water is always trying to get into the cells from hypotonic to hypertonic, but because the cells have a cell wall, they're not going to burst. The cell wall actually protects them from bursting by providing reinforcement, and so only so much water can enter the cell, and not so much that actually allows the cell to burst or cause the cell to burst. So basically, every organism on the planet except animals is going to like to be hypertonic as compared to its environment. And so therefore the environment's hypo and water tends to come into a cell. If you take an animal cell and put that into a hypotonic solution, that animal cell is going to have a problem. Because the animal cell, of course, does not have a cell wall. And if too much water enters the cell is actually going to burst. Right, so the force of water entering into a cell exerts a force that's referred to as osmotic pressure. Depending on how strong that force is, a cell can actually burst as a result. So if you take a cell, again, in a hypotonic solution, which means the cell has to be hypertonic, water tends to enter the cell, and that cell will burst unless it has some kind of reinforcing structure around it like a cell wall. All right, so in those kinds of organisms, the force of water coming in is balanced by the force of the cell wall forcing water back out again, and that provides kind of like a happy medium for those cells to exist in that hypotonic environment. So bacteria, archaea, fungi, plants, and all the protists that have a cell wall, because not all protists have a cell wall, but for those that do, all of those organisms like being in a hypotonic environment. And the other side of that coin is they for themselves are hypertonic as compared to their environment. Okay, so comparing two solutions to each other, the one that has proportionally more water is hypo, the one that has proportionally less water is hypertonic, and water goes from hypo toward hyper. Animal cells like to be in an isotonic environment, so the amount of water coming in is balanced by the amount of water going out, and there's no net change in water coming into those cells or being lost from those cells. So animal cells like the isotonic environment. And really no cell likes being in a hypertonic environment, because if it is, it's going to be losing water, and beyond a certain point, that can actually be fatal to a cell if it becomes too dehydrated. That can actually be very bad for a cell. So if we look at some blood cells here, right, these are red blood cells. These are what red blood cells normally look like as viewed through a scanning electron microscope. They're more or less round, but they have this concave side on both this side and the back side of this cell. So red blood cells are usually described, at least in mammals, as having a shape of a biconcave disc. It's a round structure that's indented on both sides. And there's actually really good reasons for that indentation that we don't need to get into right now, but anatomy and physiology, we cover that a bit more. But for now, we're just going to say that's what they look like when they're happy. So a red blood cell in an isotonic environment, the water coming in is balanced by water coming out, and the red blood cell maintains its proper shape. If we take a red blood cell and put it in a hypertonic environment, thereby making the cells hypotonic, water leaves the cell, it enters the solution around the cell, and the cell is going to shrivel up and dehydrate. At that point, the cells take on kind of this spiky star-shaped appearance, which is not normal for red blood cells to have. This appearance is described as being crenate. So Crenate. These cells have lost water, they've shriveled up, they've dehydrated, and they are now crenate in appearance. And then finally, if you take a red blood cell and put it in a hypotonic solution, so the blood cell is now hypertonic, water enters the cell, osmotic pressure increases because the cell does not have a cell wall to protect it, eventually it's going to burst as a result. So that's actually not a place you want to see red blood cells either. This slide kind of compares the red blood cells, again, individual red blood cells versus plant cells. Again, no cell really likes a hypertonic environment because in both cases they're going to shrivel up and lose water, which is not good. In the isotonic environment, the red blood cell is happy. The plant cell is okay. It's not great. It could be better, but it's also not too bad. It's not like it is over here, for example. And then in a hypotonic environment, when the cells are hypertonic, water rushes into the animal cell here, causing it to burst, versus a plant cell where water comes into the central vacuole, fills it up like a balloon, but because the cell wall reinforces the cell, it's actually not able to burst as a result. So, general rule of thumb, things that have a cell wall, like a hypotonic environment, things that do not have a cell wall, like an isotonic environment, and no cell really likes a hypertonic environment. So, a couple questions to think about here. This is a good one to think about. Why shouldn't you drink salt water? Essentially, what's happening here is if you drink salt water, which has a much higher concentration of sodium and chloride than the environment outside your cells, you're essentially filling up your intestines with a hypertonic solution, which is then going to suck water out of the cells that surround your intestine, causing them to dehydrate, and eventually take water out of other cells as well, so that you actually dehydrate by drinking this water. If you were to be stuck on a desert island and you were to drink salt water, you would actually die of dehydration faster than if you drank nothing at all, because the salt water actually pulls water out of your cells as a result of the high concentration of salt in that solution. The other extreme is what's called hypernatremia, or water intoxication. All right, so we're going to skip through these slides here, and then we'll talk about hyponatremia. So hyponatremia occurs when somebody drinks a massive, massive amount of fresh water. And I don't mean like a couple of 20-ounce Dasanis here. I'm talking about like 5 or 6 gallons of water over the span of maybe 10 or 15 minutes. Way more water than anybody would normally drink in a single sitting. If that occurs, if someone drinks that quantity of water, it's kind of the opposite of the saltwater thing. They're now filling up their intestines with a hypotonic solution. Therefore, the cells in the body are hypertonic. And as we know now, water always goes from hypotonic to hypertonic. And those cells in the body are going to start to burst, specifically in the brain. Right? So you're going to start actually having a loss, plasmolysis of cells where they break open as a result of water rushing in. Now, what that does to a person who's experiencing this phenomenon is it makes them act as though they are intoxicated, as with alcohol. So they lose their balance, they lose coordination, they start slurring their speech, their mood changes. All of these symptoms are a result of damage that's being done to the central nervous system as a result of neurons bursting because of their hypotonic surroundings. Not a good situation. People have died from this, not very routinely, but it does happen. In various cases of like college hazing, or sometimes like long distance athletes, if they don't know better, will drink too much water at the end of a race or a run or whatever. Which those folks typically know not to do that, so it's not very common in that group. People that are on ecstasy really commonly, not really commonly, but have suffered from this as well, because that particular chemical alters the way the hypothalamus is functioning. It's going to make you feel like you're thirsty, and really no amount of fluid can satisfy that thirst. So people in some cases will just continue to drink and drink and drink and drink water until eventually they start causing damage to, like I said before, their nervous system. If it gets to that point, a lot of times that damage is irreversible and can be with the person over the long term, as well as it can actually cause death too. So what we've covered so far is passive transport. Simple diffusion, facilitated diffusion, and osmosis. Things that those types of transport all have in common is A, they're passive, which means they're not requiring energy. B, they only work for hydrophobic molecules. And C, they're going with a concentration gradient. Okay? So all of those things make this passive transport, no energy required. If it's simple diffusion, you need a protein to allow the stuff to move. It's just moving right through the bilayer. But in terms of facilitated diffusion or water, which are more hydrophilic, they're going to have to use some form of facilitated transport to get across that lipid bilayer. Right? So they're still moving with a concentration gradient. They're still not requiring ATP, at least not directly. There's some ATP spent to build the transport protein, but in terms of allowing this stuff to move across the membrane, no energy required there. These are passive processes. So just a quick review here. Facilitated diffusion, we've got glucose here, which is very much hydrophilic, bonding to a carrier protein. Carrier protein is changing shape, dropping off glucose inside the cell, and then returning back to its original shape to pick up the next glucose in line. So that's a facilitated diffusion example. So when we pick up the next section, we're going to start off by talking about active transport. And so if passive means that energy is not required, active means that energy, more specifically ATP, is required to make that form of transport happen. So we'll wrap up this section now and pick up the next one in just a second.